Hi everyone, and welcome to the second video lecture for Chapter 17, Microscopes for Trace Evidence. The most common type of microscope used in trace evidence analysis is the stereo binocular microscope. This microscope is used to provide preliminary evaluations of trace items, as well as to aid in the recovery of trace evidence from large pieces of evidence. Stereo microscopes have two lenses, the objective lens and the eyepiece lens. The total magnification power of the stereo microscope will depend on the specific optics of the lens, but typically these microscopes can magnify an image between 25 and 1200 times its original size. When using the stereo microscope, the eyepieces function separately, but because they're viewed at the same time by both of your eyes, they allow for a three-dimensional image similar to that created by our own eyes when we're looking at something. Another common microscope used in trace evidence analysis is the polarizing light microscope. A polarizing light microscope is the same as the basic microscope we just discussed, but it adds a polarizer and an analyzer component into the microscope so that it changes the way that the light goes through the sample. Polarizers are why some sunglasses help with glare from the sun and objects more than others. If sunglasses are polarized, what happens is they filter out some of the light coming to your eye, and they only allow light traveling a certain direction to actually reach your eyes. This reduces the glare far beyond what sunglasses with just a colored filter can do. Depending on the specifications of the polarization, the light can become partially or totally polarized as it goes through the sample. This level of polarization, as well as the characteristics related to reflection, absorption, and propagation, can help analysts determine what type of sample they're dealing with without having to destroy or damage the original piece of evidence. A spectrometer is another instrument that can be added to a microscope to aid in forensic analysis. A spectrometer is designed to measure color. So when used in a microscope, it allows for what is known as microspectrophotometry, or an area of microscopy focusing on the identification of color within a substance. Unlike color matching with our eyes, microspectrophotometry, try saying that 10 times fast, microspectrophotometry can provide an objective, quantitative assessment of a colored object, and it allows for comparisons of minute color differences that are not visible to our naked eyes. The comparison microscope is another type of microscope that's used in forensic analysis. We've talked previously about how a comparison microscope is used to compare unknown and known samples. Here you can see an example of how the ballistic comparisons we've discussed previously are obtained using a comparison microscope. The comparison microscope consists of two independent microscopes, each with its own staging plate and focus knob. These microscopes are linked by an optical bridge so that the image that's seen by the person using the microscope includes both independent images superimposed over one another. The final type of microscope I want to discuss is the scanning electron microscope. This is one of the most powerful microscopes that we've developed to date, and the advancements in SEM have allowed us to observe things unidentifiable using only light microscopy. Scanning electron microscopes can magnify an object up to 100,000 times its original size. The way SEM works is by sweeping electrons over the surface and then measuring signals produced on a detector. The signals measured include the secondary electrons, the backscattered electrons, and the characteristic X-rays, all of which are described in your text. As you can see from the images here, SEM develops some of the most detailed, precise images of microscopic particles and objects to date. All right, well, that concludes the second video lecture for Chapter 17. Join me in the next video lecture as we explore the process of hair and fiber evidence.